today we're going to go through a lot of this. Hopefully will be a great deal of review. Did you get that up and running? Perfect, thanks. Hopefully a lot of this is going to be review concepts that you already know, but again, I can't emphasize the importance of fundamentals, having a good conceptual grasp on some of these types of concepts. Everything we do builds on one another, and so if we miss or are not on the same page in terms of some of the fundamental stuff, we're going to be off base down the road. Okay, so today, talking about basic distributions, frequency distribution, central tendency, measures of variability. This is going to be important. Variability screws with people. People have a hard time getting this idea tacked down in their head. So we'll spend some time there talking about shapes of different distributions, graphical representations, just basic building blocks. So we'll move through this pretty quickly, but if we hit something and you guys slow me down. If I've moved on and you don't have a good grasp of something, shoot a hand up and say, hey, stop, go back. You're probably not the only one, okay? So, talking about basic frequency distributions, not a lot of new business here. If we're talking about our frequency distribution, just some sort of tabular organization of numbers, identifying the number of individuals associated with a certain category of measurement. What we're doing here, just synthesizing, communicating data. These frequency tables are nice, and I would encourage you to think about using these even in your own, even in the problem sets that we'll do. Tables are a nice way of just very efficiently and succinctly putting down information, right? I could spend a whole paragraph of manuscript talking about the characteristics of my data, but it's probably a better and more efficient way just to have a table with your demographic characteristics and just lay it out there and maybe identify a couple big pieces. Say sample was primarily white, non-Hispanic, and female. Average age was this. Full sample characteristics are available in table 1, right? Just a nice way to communicate data. Here, what we're doing, showing clustering spread of scores, position of an individual score within the rest of the distribution. So, what type of data are we demonstrating or are we displaying here in this table, Angela? What's the level of measurement for the race variable here? What kind of variable is race ethnicity? It's categorical, and specifically what type of categorical variable? No, categorical. Someone help her out? Nominal, right? Okay, there's no natural order to the levels of measurement in this table, right? It's just a name-only type of thing. And so here, this does a nice job of demonstrating. Looks like our sample is predominantly white non-Hispanic. We've got a reasonable contingency of black non-Hispanic individuals here, Hispanic, Latino, Asian, and then a small number of Native American individuals here, right? Versus the table shown here. Lauren, what's X?
The frequency, or no, category.
The category,
sorry.
right? The category of something.
Yes.
We don't know, right? And it's difficult to tell with this table what level of measurement. It looks like maybe this is some sort of ordinal scale, right? But we have scores ranging from 5 to 10, and then we've got just a very rough display of the distributions, right? So we can say most people are scoring 8, but we have reasonable distribution of scores around that, right? So here we're looking at, if you say, oh, where does a score of 8 fall in this distribution of X, you can say, well, it looks like that's kind of somewhere about in the middle of the distribution here, right? So sometimes we'll, oftentimes the level of types of variables that we're displaying in our frequency tables are these types of nominal variables, but we can also start to tweak these to start to incorporate more continuous types of data within our frequency distribution. So our X is a category, F is our frequency, and our frequencies can be numbers, they can be proportions, they can be percentages, just depends on how you want to format this, what makes the most sense in terms of communicating information. Okay. Any questions on our frequency tables? Yeah.
Just another thing.
Mm-hmm.
The word values refers to the scores or frequency, because I see that word thrown around a lot, and I get kind of confused with it.
where are you saying?
No, I meant in the textbook when they talk about things like frequency or something, they say like words like values. So I get confused as if they're actually talking about the scores or that frequencies.
Probably depends on the context, right? So if we would say, if I was looking at the frequency here, I'd say the values or the figures or the numbers and things. I think you're probably using that interchangeably. So yeah, just kind of look at the text or use the context of the text to determine what they're talking about values. Because I mean, your categories here could be values, right? So these are values. These are values on this of the whatever X scale is. The frequency are also values, so you just kind of have to make a determination based on context. Other questions? Cool. All right. Where these things start to get a little bit more, you have more options, more decisions to make when we start to transition into group frequencies. Here are group frequencies are ways we bend frequency tables to our will in order to incorporate or accommodate continuous data. Couple things to think about here. Class intervals. This is the interval used for our grouping categories, okay? Class intervals are the chunks that we're using to break up this continuous scale. Individual bins, by definition, or by contrast, identified by the upper and lower limits of the class interval that we're using. So in this example here, this income data, what's the class interval? What do you think, Morgan?
0 to 9,999 and upwards, each of those categories.
Okay, so 0 to 9, is 0 to 999, is that a class interval or is it a bin? That's a bin. What's the class interval?
0 to 80,000.
What's that?
0 to 80,000.
Not quite. So what's our class interval? What's the interval we're using to group categories of income in this table? Yeah, functionally $10,000, right? So our class interval here, $10,000 with individual bins from 0 to 999, 10,000 to 19,999, right? And so if we're thinking about the class interval, I've got this continuous, this truly continuous variable that I want to reduce down into a frequency table. What I need to do very first is start to think about what are the chunks that make sense given this interval, right? Here we've got intervals of 10,000 and censored at 80,000 and above, okay? But what happens, and we're going to talk about some rules and trying to think about how we fashion this in a way that makes meaningful sense and communicates things importantly. Is there anything that says we have to use $10,000 as our class interval? No, we can make it whatever we want, right? We can make it 50,000, right? But what's going to be wrong? What's going to happen if I make my class interval 50,000?
For distribution.
The distribution is going to be kind of wonky, right? What else is going to happen? Yeah.
You're going to use a lot of the individual scores.
Yeah, right. I mean, I'm basically saying the person who makes $0 and the person who makes $50,000 belong in the same category, right? And so wanting to think as you're starting to create your class intervals, think about the construct that you're trying to capture and what makes sense to reasonably start grouping people into sections, right? So $50,000 is probably not great. What about $1,000? What's wrong with that, Sam?
Because there's like 80,000.
This is going to start to become problematic, right?
Yeah.
I'm comfortable with proposition, the person making $22,000 a year and the person who's making $23,000 a year, sufficiently close enough to put those in the same category, right? And so this is where when we start to, and you see interesting things when people start submitting theses and dissertations and research publications for review in terms of how they're breaking things up, right? So you want to think about, based on the construct that I'm trying to summarize for people, what makes sense in terms of my class intervals, okay? And so again, this is an actual example from some data we collected in my graduate lab, looking at annual income in people who are coming in with post-traumatic stress disorder and chronic pain, right? Someone tell me make an interpretation of this frequency table. How would we describe income within this sample? What do you think, Alex?
How would you describe?
Yeah.
It's numerical.
Okay, what are the characteristics of income in this sample, would you say, based on the table here?
Higher income is less.
Okay, so it looks like we start to see people trailing off as we start to get into higher income. How else might someone describe what we have going on in this frequency table? Yeah.
Is it positive?
A little bit of positive skew. But really, probably the skew isn't the sort of defining feature of this distribution. What's this distribution kind of look more like? What do you think? Or Katie, what do you think?
Would it be by number?
Yeah, kind of. I mean, really, our mode is right here. I mean, it's looking like, if we're looking at this, we've got kind of a pretty even distribution across different income strata, right? To me, if I'm looking at this, looks like, I mean, we do have a tail on the positive bin, but I mean, 28, 34, 31, we got a little dip here, 25. It looks fairly square, right? And so, like, I wouldn't call this a normal distribution, but these are the types of things we can go through and start to surmise based on the frequency distribution, right? And we'll work in and start talking about graphical methods of looking at some of this stuff in a few slides. But yeah, it looks like, you know, most people are running from about 0 to 60,000 a year, with a handful of people making more than that, right? So certainly, it looks like we have low to middle income people in this group, right? But not any huge, certainly not demonstrating a normal distribution. And we do have technical modes, right? But it's looking pretty flat and even across the board, right? So these are the types of things we want to not just say, oh, you know, this is the percentage of stuff going on. Wanting to start thinking about ways we can describe the data based on some of these frequency distributions. Okay, questions? All right. So some general rules to think about when you're trying to create a frequency distribution in data that constitutes a continuous variable. Group distribution, somewhere about 10 bins. Okay. So what you want to do is you want to select a class interval that gives you probably somewhere in the vicinity of 10 bins. Now maybe that might change from situation to situation, right? You don't want necessarily to have a demographics table that spans 3 different pages, right? And so maybe you cut this down depending on what makes sense. But in general, less we lose too much information. More than that, things start to get too complicated. And so wanting to think about what's the class interval that's going to give me a reasonable number of bins. Okay? Rule 2, want our class interval to be a simple whole number, right? 2, 5, 10, 100, right? Given the nature of the scale, right? What was our class interval for the income example? 10,000, right? It wasn't 10,004 because that's weird. Right? Just a nice simple number that's easy for people to get and surmise. Intervals should be the same width. It should cover the range of scores so that each score fits in only one category. So here, for the limits of our bin, we're talking about the real lower limit. This is the smallest absolute value in the data set that's going to fit into this bin. The real upper limit is going to be the largest value, right? So if my bin is 0 to 999,000, right? Maybe, and I'm not sure if people are going to be reporting at this level of precision, probably not. A real lower limit is real lower limit. You can't make negative income. Well, I guess you can't make negative income, but people simply don't report debt on their demographics, right? So the real upper limit for this might technically be 9,999.49 cents, right? That we would round down into this bottom bin versus if you make, you know, a penny more than the next person, you can get rounded up into the next category. Right? So we're thinking about real upper lower lower limits, and then upper lower limit of bin should be easily divisible by the class interval. Okay. So let's say we have a class interval of 10. So bins are going to be 0 to 9, 10 to 19, or 1 to 10, 11 to 20, something like that. Your upper limit or your lower limit of your class should be divisible by your class interval. Okay. So again, here, if we're thinking about this, our class interval is 10,000, right? Here, 10,000s, you can divide 10,000 into 10,000. You can divide 20,000 by 10,000, 30,000 by 10,000, right? So then everything starts to come and make sure everything sums to 0, okay? So all these things seem pretty self-explanatory. You're like, yeah, sure, why not, right? But you get sometimes weird stuff, right? So we've got miles driven per day, right? Stephanie, tell me what's wrong with, is this a good or is this a bad frequency distribution?
It's bad.
Yes, why is it bad?
Because there are too many ones.
Yeah, so our class interval is too small, right? It looks like we've got 1 mile, right? There's probably a level of precision that we don't need to reasonably describe this data, right? Okay. What about, Rajiv, what about this distribution here? Is this good or bad?
It's good.
It's good?
No.
Why is it not good?
The class interval are really, really big.
Okay, so,
So we want to.
yeah, it starts to be tough. Like the person who drives 50 miles a day and the person who drives 100 miles a day, should they belong in the same class? I don't know, maybe, right? But it is a little thin, right? If our target is somewhere around 10, 4 looks a little rough. What else is problematic with this? Yeah.
They're not the same size.
They're not the same size, right? So this is 50, this is 50, that's 100, that's 250. That's not good. What else? 70?
That if you're driving 50 miles, you can fit into 2.
Right, we don't have mutually exclusive bins here, right? So if someone drives 50 miles a day, I don't know where they go. One other thing, what's wrong with this? Lots of stuff wrong with this.
It skips.
Yeah.
So it's from 100 to 150.
Yeah, what about the dude who drives 120 miles? Where does he go, right? So maybe, you know, the real lower limit on this is 125 miles? That's weird, right? And so we've got some problems there. Excellent work, all right? What about this? Is this good or bad? What do you think, Angeline?
Good.
Might be
Well,
better.
It's better because it has a lot of the features, but the lower interval is holding the majority of the.
Okay, so we've got kind of a skewed distribution
Yeah.
here, right? What else makes this an awkward table? Yeah.
There should be more zeros to make it look better.
More and more zeros, what do you mean?
Like, if it was like all ending in zeros, it'd look,
Okay.
you
so
have more better like understanding.
Right, and so what, in terms of those rules, what specifically is going wrong with this?
It's all ending in like 3, 5, 7, 4.
Right.
9.
Basically our class interval isn't divisible by our things, right? And so this is kind of a presentation thing, it's kind of arbitrary, but we tend to be more comfortable if things are ending in sort of whole numbers, working in 10 units of 10s or 5s or something like that, right? So, you know, the cut point between 44 and 45 seems kind of arbitrary, right? So it's, and so we can't divide 3 by, well, I guess we can,
Yeah.
right? But it's on a weird scale, right? And then also, we've got a bunch of 0 values here, right? And it looks like we've just included those to get our way up to whoever falls in this 129, 149 thing, right? how might we, so really, here's the people we put our frequency table to accommodate the outlier. These are real data points that we want to keep in the set. Probably what's a better way to do this than have a bunch of empty categories working up to that value.
87.
What's that?
It's labeling 87 and over.
Basically turning this into a censored variable, right? We say, all right, we've got 87 greater than 87. That's still weird because 87 is a weird number to have in a table. But, right, instead of having all these missing categories with no variables, just say this amount or over. Okay. All right. What about this table here? How do we feel about this? Is this good or bad? What do you think, Lauren?
Good.
Good. Yeah. Why is it good?
It has like over 10 bins
Mm-hmm.
and the intervals are the same.
Mm-hmm. Everything's divisible by 10, right? We got one sort of missing category here, but that's fine. It's just one gap, right? And we've got a couple categories that are above, right? And so this would probably be the best example going on here. Now, if this is part of a larger demographics table, this might be a little more fine-grained than you would want, but sort of up to you to determine sort of the level of precision here. We could easily, you know, choose some other type of thing. And maybe this makes sense if we're talking about driving in adolescence or something like that. So this is, you know, maybe this makes sense, the level of precision makes sense if we're looking at new drivers and how far they're driving and things along those lines, okay? So again, wanting to think about, as you're representing these data, you're like, oh, frequency table, that's pretty easy, straightforward, but a lot of times we wanting to think about how we're going to go through collapsing, what are the categories we're going to make, what are the class intervals, so that we get something that makes reasonable sense and is pleasing to the eye, okay? Questions on any of this? Cool. All right, getting our frequency distributions in SPSS, pretty straightforward. Show of hands, who's familiar with or has at least used SPSS at some point in their life? Okay, so 3 people who haven't, that's fine. It's an easy, you don't have to learn a specific programming language to get this to do what you want it to do. And we'll go through plenty of tutorials to make sure that you're on point with stuff. But in your SPSS interface, what you'll do is you'll go up here to Analyze, drop down Analyze, you'll choose Descriptive Statistics, you'll choose Frequencies, and then what you do is you just go from here, find the variables that you want frequency distributions for, and drop those into your variables, and then go ahead and hit OK. One thing you'll want to recognize is that your frequency tables need to be limited to categorical data. Depending on what version of SPSS you get, you see this this type, right? Or it's actually it's this way. Sometimes if your variables are labeled as not continuous or categorical, sometimes it won't give you an option to select this stuff. What more often happens is you'll drop a continuous variable into this, and if I've got sort of overall wellness ratings on 0 to 100, and you ask SPSS to give you a frequency table for that, what's your frequency table going to look like? What's that?
It's like 10 more.
Yeah, it's gonna be long, right? So everybody who entered 53 in there is gonna have a line and so on and so forth, right? So just want to be careful about what you're requesting there. So some examples. So here's a case where and sometimes your bins are gonna be determined by the data that you collected, right? Looks like here we have information on employment, right? And it looks like what we collected was no employment, 1 to 10 hours a week, 11 to 30, over 30 hours a week. And that's kind of what we're left with based on the data that we collected, right? And so we've got the frequency, the number, we've got the percent, the valid percent. What's the valid percent? That looks, numbers are a little bit different than the percent. What do you think, Stephanie?
The number of values that were entered correctly for that, or?
Not entered correctly, but for the number of cases that actually have a number in there, the proportion, or the percentage of that, right? So, it's actually pretty much the same, because we've got over 1,000 people and only one missing value. But basically, this is taking this number divided by the total number of actual values in here versus your total percent will calculate in the number of the percentage of cases that don't have a value for that variable. So your valid percent, cumulative percent, what's cumulative percent? What do you think, Alex?
Cumulative percent is normal to variable.
Yeah.
So it goes within that specific.
And this might not be something that's relevant to you, but again, as we go through these SPSS outputs, I want you to be able to identify and describe everything that it's giving you. So this is, so we've got 57.3% of the sample reporting no employment, 64.3 reporting either no employment or 1 to 10 hours, so forth and so on. Okay. Same thing here. We have marital status, categorical variable, married, separated, divorced, widowed, never married, cohabitating. So we got 10 values missing here, but again, giving us, if we want to just write down the percent and include a footnote in our table that says percentages may not sum to 100 given missingness in the data. Probably a better way to go about things than reporting your valid percentage, because then you're making it sound like you've got all data when you actually don't. So, okay. But this is a basic SPSS output for frequencies. Make some sense? Cool. All right. Other thing we want to transition in here is to start talking about measures of central tendency. In general, if you talk about a measure of central tendency, talking about some figure, some number that best describes the center of our distribution. Okay. Conceptually, with our measures of central tendency, and this is really important, right? We want to keep in mind what we're trying to do with this and not randomly pick a measure of central tendency out of thin air. What we're trying to do is find one score. What's the single score that's most typical or most representative of the group, right? If I had to say, here's my variable, and I need to choose one score that's most representative of the characteristics of my sample, what is that score? What is the score that I choose, right? This starts to become important. This is our common statistic. This is the marker we're going to use for our between and within group comparisons. Okay? So I've got group this, and I've got group this. What I want to say is, what's the most representative score for this group? What's the most representative score for this group? And do I have enough data here or evidence to say that the best score or most representative score for this group is different than the most representative score for this group? Okay. And if you remember what we're trying to do with these measures of central tendency, it will help you conceptually think about which one is probably going to be the best approach in terms of what we're doing, because no single method for determining what the best measure of central tendency is going to be. Okay? And again, leading into a lot of this ambiguity that we're going to deal with this entire year in terms of these are my options, which one of these is going to best suit my purpose. Okay? So, in this situation here, Rajiv, where's the center of this distribution?
$100?
100. It's pretty straightforward, right? It looks like, if I'm looking at it, like, not everybody scores 100, but if I had to say, this is kind of the middle of the distribution, the most representative distribution, it looks like most people in this sample scored 100. That's probably going to be my best bet, right? What about this? Where's the center of that distribution?
So, 0?
Well, maybe. 0 is the most representative, right? But where's the actual center of the distribution? Maybe -2-ish, you know? It starts to become difficult, right? Because we got this tail moving off in the we got some negative skew here. And so, yeah, I don't know, maybe somewhere around there, right? What about this? What's the center, what's our measure of central tendency for this distribution? What do you think, Katie?
What do you want to use the node
What's that?
What do you want to use the
Maybe, right? But if this is my distribution, what's the middle? 160, right? 160 is technically about the middle of the distribution, but is that a very representative number? No, because we actually have very few people scoring at that level, right? And so we start to get into problems and thinking about, like, what's the one single measure that's best describes what we've got going on, right? What's probably, if this is body mass, what do we probably have going on in this sample here? Yeah, we've got a couple of populations, right? And anytime you're looking at a bimodal distribution like that, the first thing that should come into your mind is saying, have I actually sampled from two distinct populations? Because that's what it looks like is going on here. So, again, what we're doing when we're going through selecting a measure of central tendency, some things we want to take into consideration, shape of the distribution and type of data. These are the two things that are probably going to help us figure out what specific measure that we're going to use. And probably the most common and the one that we'll work with the most is going to be the mean, right? Mean is described or identified in statistical literature as your first population moment. A moment is just a characteristic of a distribution. Mean, first population moment. Mean is the sum of scores divided by the number of scores. Population mean, you take all the members of the population, sum them up, divide them by the number of people in the population. Sample mean, calculated the exact same way. No difference in the calculation of the population mean versus the sample mean. Okay. What do we call the mean if we're talking to our grandma? The average, right? Okay. Your mean is your arithmetic average here. Yeah.
Oh, I missed the point about the moment. What's the moment again?
It's just a characteristic of a distribution. When we're talking about distributions, there's several moments. The mean is the first population moment. Your variance is the second population moment. Skew is the third. Kurtosis is the fourth, right? So it's just different characteristics of your distribution from a mathematical standpoint.
That's by like importance, the way you put it, or is it just?
No, it's just what they're labeled. Okay, so yeah, don't worry about this. Is just more. So this is bar trivia, right? when someone say, "What's the third population moment of distribution?" Back skew. Skew. I got that one right. I'm attributing my team. Okay. All right. We can also. So this is just the straight mean. We can also calculate a weighted mean. This is what we're going to do. Find the total average of two different samples. This is a little bit different. What we're going to do is we're going to take the sum of all values in the first sample plus sum of all values in the second sample, divide it over the two samples together. Weighted mean is not the average mean of the two sample means. Okay. Why can't we say, all right, I've got a couple of different samples. Here's the mean of sample 1. Here's the mean of sample 2. I'm just going to take the mean of those two samples and get the weighted mean.
Because you're dividing it twice.
You're dividing it twice. What's conceptually, from a practical standpoint, where might we get in trouble if we just take the mean of sample 1, the mean of sample 2, add those two means together and divide it by 2?
Be a different number of.
Perfect, right? If our samples are a different size, right? If I've got 10 people in sample 1 and 50 people in sample 2, right? The number I get, the weighted mean, particularly if the mean of sample 1 and the mean of sample 2 are quite different, the number I get for my weighted mean is not going to be the same as if I just take the average of sample 1, the average of sample 2, and take the average of that. Okay. When can I take the average of sample when can I take the average of the mean of sample 1, mean of sample 2 divided by 2 and get the same as the weighted mean? When they're the same size, right? But in general, and this is when we start calculating pooled variance estimates, this is going to be important, right? We've got two samples, right? And presumably, if we've got two samples from the same population, and one sample is a sample of 10, the other is a sample of 50, which is the better estimate of the population? sample of 50, why?
Because it's representing more.
It's got more people, right? It's gonna be a more precise estimate. And so if do we want to treat the sample of 10 and the sample of 50 equally? No, we want to give more weight to the more precise estimate, right? So again, this is something to be careful with, recognizing that if I have a couple of different groups and I just take the average of this sample and the average of that sample, let's say I've got two different studies, right? I've got Angeline et al. 2017, and I've got Lauren et al. 2017, and so you have a mean of 53 and you have a mean of 48. I'm like, oh well, I'll just add those two, take the difference, divided by 2, take the average, and that's my mean, right? Maybe your sample is considerably smaller sample size than your sample, right? We want to take those things into account as we're calculating sort of what the average of those scores is going to be. Okay. Questions on this? Perfect. Okay. Some characteristics of the mean. This is going to be important. Every score in the distribution contributes to the mean. Every single person who we've collected is going to start to influence the calculation of the mean score. If I change a score, I'm going to change the mean. If I add a new score, it's going to change the mean. Okay? This is always true. When is this not true? What are the boundary conditions of that? When can I add a new score and it doesn't change the mean? If it's the same as the mean, right? If my mean is 50 and I add someone and their score is 50, then it's not going to change the mean, right? But in general, and this will start to become relevant as you're screening data or doing things, right? Like, oh, I ran all my analyses, but then I realized that I actually shouldn't have included these two cases. You need to go back and recalculate things, because if you remove those two cases, unless those two cases are exactly consistent with the sample mean, which if they are, I'm not sure why you're removing them in the first place, it's going to shift things around and start to change things, right? So adding a score or changing a score is going to change the mean, but what we can do is we can add, subtract, multiply, or divide every score by a constant, and what that's going to do is it's going to change the mean by the same factor of the constant, okay? And this starts to become common when we're starting to try and go through and rescale things, right? So if I have a mean of, the mean of my sample is 20, and I add five points to every score, Lauren, what's the new mean of my sample? 25, right?
So we're thinking.
Right, yeah. If I divide every score by 2, what's my new sample mean? 10, right? Same thing, addition, subtraction. If I do the same thing to every single score in the sample, all it does is it just shifts my my sample mean by that much, right? And if you think about this in terms of, I've measured something in terms of, not people, no one is 12 inches high. I've measured something in terms of inches. I want that to be feet, right? All I need to do is divide my inches by 12, that gives me feet. And now my mean here is going to be 48, my mean is now 4, easy peasy, okay? Thing to remember, addition, subtraction, division of every score by a constant doesn't change the overall shape of the distribution. This distribution is exactly the same as this distribution. All we're doing with the rescaling is we're just changing the numbers down here at the bottom. And so let's say you collect time since some event in terms of months, but that starts to be not terribly precise, and telling people or reporting things in terms of months maybe isn't the most efficient way to do things, and you want to describe things in terms of years, right? So you divide your months variable by 12, and now you've got years. Did you change the distribution of scores? Or if you got a wicked outlier that's hanging all the way out there, did that fix that outlier if you divide everything by 12? Nope, distribution is the same. Okay. So again, something that commonly happens when we're working with scaling. Okay. So questions about the mean, characteristics of the mean, things that impact the mean. Comfortable with the mean? Good, we're gonna be using the mean a lot. Right? Other measure of central tendency is gonna be your median. Calculate the median. What we're gonna do is we're gonna take all the scores in our sample, we're gonna line them up in order, and then we're gonna select to identify the median, the score where 50% of scores fall above, 50% of the scores fall below. So here we've got scores 1 and 9. We line them all up in order, and we say here we've got 15 scores. 3 is the middle. This is our median. We've got 7 scores above, 7 scores below. With an odd number of scores, we lift scores from the highest and lowest, select the middle score. If we've got an even number of observations, what can happen is what we're going to do is we're going to select the middle pair, and the median chosen is the midpoint of the values, right? If we had 16 values and this was 3 and the next one was 4, right? What would our median be? 3.5, right? And so with an even number of scores, it's possible that our median might not actually be an observed value, okay? But not always. What happens if my 15th score was another 3? Then what's my median? Still 3, right? But what we can get if we have an even number of scores is a median that doesn't actually fall. But if you've got a large sample, you've probably got several of the same scores that are camped out right there in the center, and so it typically is not an issue if you've got sufficiently large samples. Okay, questions about the median? All right. Mode, score category with greatest frequency. We can use mode with any scale of measurement. Okay. We can also have distributions that have multiple modes. Say this is bimodal, this is trimodal. We can have distributions that have relative modes. Technically, the mode here is 4, right? If this is drinks per week, our technical mode here is going to be 4 because it's the category, or it's the value with the most values. Sam. And so, but we've also got 0, which is prominent enough that we should probably identify this, right? So we call this a major mode and a minor mode in this distribution. So when do we choose what index as our measure of central tendency? Our mean, this is going to be what we're shooting for in most cases. Why is that?
You could manipulate it and do math on it.
Okay, so we can manipulate it, and it's nice for a lot of different reasons. In general, based on our system of science, what might be the reason that we're predisposed to be looking to use the mean?
It takes all values into account.
Takes all values into account. What else? Our inferential statistics are inherently mean-based almost always, right? If we're not going to use mean values, then we're starting to drift into weird non-parametric statistics that that are good in some circumstances, but are going to be, we're not going to be using non-parametric stuff as much as our mean-based statistics, right? It's kind of what we're hoping for when we're doing t-tests, ANOVAs, regression stuff are all mean-based statistics, and so hopefully we're going to be wanting to use the mean. But means often providing representative value for the set. We've got every score in this distribution contributing to the mean, right? So everybody gets a say. Mean is very democratic that way. One thing that's nice is we've got better stability across samples relative to the median and the mode, right? Again, median is based on what score happens to fall in the center of the distribution. So across replications, that median, that value of that median might jump around a little bit. Mode is technically dependent on what category has the most values in it, right? And so again, that's can start to jump around. Your mean, while it won't be exactly the same number, is probably going to be pretty close, more stable across samples. And again, this is going to serve as the basis for most of our inferential statistics. Even when we get into things like correlation and regression, these are still technically identified as mean-based statistics because calculation of your variances and covariances are dependent on sort of that mean value. Okay. Limitations of the mean, though. Easily influenced by extreme scores. You get a wing nut out there and it's dragging the whole thing out and around. And so despite, so this is both the strength and the limitation of the mean, all values contribute, but single values can start to pull things out and start to skew our estimates of the most representative value. Value may not actually exist as an observed score. We're typically not often worried about this in general, but if you did want the most representative value to actually be a value that you could actually get, this might start to become problematic. This is something we don't often think about, but we should more often. Interpretation of the mean is relying on the assumption of interval data. Someone tell me what that means. Why is that important and relevant? Or why, if we're calculating mean, are we assuming an interval level of measurement? Thoughts, Rajiv? No thoughts. Take a guess. So why might it be important? And we're going to attach some meaningful interpretation to the mean that we're working with. We're assuming interval level of measurement.
Will you include all the division?
So if I say average graduate student income is $16,254 a year and 34 cents. We're very quite specific. Does that mean something? Does that mean something? Does that have a real practical interpretation? Yeah, right? What if we say 34.5, right? So you have fractions of a cent. Is that still meaningful? Yeah, it's a fraction of wealth, right? And things like that. What if I say that the average number of children in a house is 2.5 kids? Half a kid is not a thing, right? That's not a real, and so we can calculate a mean on whatever we like, right? But if we're starting to think about using this, we can start, and we don't, we ignore this, right? And pretend that 2.5 kids is a thing. But 2.5 kids isn't a thing. That's not a real unit, right? And so, again, thinking about levels of measurement and what these data represent literally. Again, I can't, if I give you sort of recommendations as you're working throughout this entire year, if you find yourself having a hard time attaching an interpretation to an analysis or data or something like that, stop yourself, take a step back and say, literally, what does this mean? Literally, what is the interpretation? Technically, what is the interpretation of this, right? And if you think about literally what the technical interpretation of 2.5 kids, it's a half a child, which statistically, we're just saying that the mean is somewhere between 2 and 3. Technically, a half a child is not a real construct among normal people, right? And so wanting to think about this in very clear terms, right? So again, when you're having trouble with things, take a step back and say, is this a real thing that exists conceptually or in real life, right? And so this is one of the things that can be problematic about them, is we're assuming interval data even when we shouldn't, right? And again, this becomes relevant with in psychology, particularly when all of our scales are at best ordinal, or we pretend they're continuous, right? Thinking about, is this an actual thing? Okay. But in general, we're going to say, well, we're close enough. We're going to try and use the median, but in some cases, median is just gonna be horribly inappropriate in terms of measuring central tendency. Median, gonna be preferable in some circumstances if we've got skewed data and we've got meaningful but extreme values, right? Again, income is a good example of this, right? We can have, again, say, graduate student, mean graduate student income is, say, $16,000 a year or something like that, but then you've got a couple people who are doing something crazy and their annual income is $30,000, right? It's like twice what the mean is, right? And there's two of them and they're hanging way out there, lucky bastards, right? But do we ignore those people? No, because they're part of the population of interest, right? Should we calculate a mean though? Because no, that's gonna drag that out and it's gonna make it sound like people are making a lot more money than they are, those of us in the masses, right? And so in this case, we don't want to ignore them because they're important pieces of information to take into account, but mean is gonna get skewed, right? So what we're probably gonna do is we're gonna choose the median. So when we've got positive skew, if we've got skewed data, and we calculate the mean of the skewed data set, will the mean always be relative to the median?
Towards the extreme right.
Yeah. Skewed data is always going to pull the mean towards the tail of the distribution that's skewed, right? So here, positive skew, here's our mean, right? But here's our median. This is our literal middle value. Mode is going to be here. Negative skew, same thing. Mean always dragged out to the tail. Median is going to be in the middle. Mode will be on the other side. Okay. So with skewed data, so this is sort of conceptual. Here's actual data, right? We've got this. I don't know what we're looking at. Some sort of score. People didn't do well in this exam, I guess. And then someone did really well with extra credit, right? I don't know what this is. But presumably, assuming that this is a real value and an important value to consider, our median is probably going to be a better bet in terms of identifying that little value than our mean, because our mean is going to be hanging out somewhere out here. Okay. Analysis involving censored data, right? Why is our median a better approach to measuring central tendency for this frequency here, or for this frequency table here? What do you think, Angela? Okay, we got an outlier, right? But can I actually calculate a mean based on these data? No, right? Because this could be 100, or it could be 200, or 500. I don't know what this value is, right? I technically can't calculate a mean based on these data because, and you say, oh, well, maybe if I have in the real data set, but maybe there's just a value where we hit 100, and anybody who has 100 miles, drives 100 miles a day or more, just gets a value of 100. We just cap it at that, right? So we've got 6 people, or I guess 3 people with a value of 100. I don't know if that actually means that they drove 100 miles or if they drove more than that. We just capped it at 100, right? It's impossible for me to calculate a true mean unless I have access to those data, right? So in censored data, medians are going to be more appropriate. And then technically, data that are involving our ordinal scales. Okay, what are the characteristics of an ordinal scale? Morgan?
I'm so sorry, I can't recall. I think it's with ordinal scales when they have even order, but the difference between categories isn't meaningful.
Exactly, right? So, and again, the best example I can give, if we're thinking technically and precisely about this, right, is our ordinal scales, our Likert type scales, right? Whether it's a personality inventory or anything, right? You say, okay, rate how much you like something or how much this describes you on a 0 to 5 scale. Well, there's no systematic distance between, I mean, on the page it is, right? And the numbers that we've assigned to those have meaningful distances between, but like the construct that we're actually capturing doesn't, right? Like, I don't know that the difference between 3 and 4 in terms of happiness for Angeline is the same as the distance between 2 and 3 for Lauren. Like, we make that assumption, but it's a ridiculous assumption, and it's clearly not true, right? Now, we pretend that it's continuous, right? We've pretended that we've calculated some sort of interval or ratio scale. We've treated it such, and that's generally fine in terms of statistical inference, but something that we should always be, if you're gonna do things that are technically wrong, I would want you to know that what you're doing is technically wrong and know why you're doing it, as opposed to just pretending that it's an okay thing to do and you've not violated any assumptions. Technically, our median is going to be preferred if we're using data without equally spaced intervals. Median doesn't assume, median-based analyses aren't assuming equal intervals between values, and so technically, in applied settings, consequences of this would mean that we would be doing median-based statistics or non-parametrics across the board, but there are downsides to that, to the point that I would not recommend people use that approach. But important to recognize that technically we're assuming continuous data, even though the data that we're collecting is not at an interval or a ratio. John, do you have a question?
Yeah, so for the sensor data, would
Yeah.
the median then be a range, or would it be like that?
Well,
How do you pin one down?
in most cases, right, if we go back to here, we're saying that we've got 3 values that were some value of 100 or more, right? But because we're calculating the median as the middle, right, all we're going to do is we're going to say, all right, we're going to count in 3 from these, and I don't know exactly where they are, but I'm just going to count in 3 and then count it. So my middle value is going to be in the middle here, and so it doesn't matter what the actual value of those 3 cases were, because we're just going to move in, we're going to count those as the 3 cases on the farthest outset, or on the farthest margin, and then move in here. So if we've counted for that these are just 3 really big values, by the time we get that down here, it doesn't really matter what those values are at all. Does that make some sense? Okay, so basically we're lining these up in terms of these cases 0 to 9 all the way up. By the time we get to the end, it's like, and some 3 bigger cases that are of some unknown value. Doesn't matter, the value actually doesn't matter when we're calculating the median. Does that make sense? Okay, cool. All right, yeah.
So hypothetically, if
Mhm.
participants answered on a micro scale, would it be more responsible as a researcher to like pre-test what their idea of like extremity would be, since it's like mic 3 may be different than term 3? Would that be like the most responsible way to do research?
It's tricky, right? And this is where your psychometrics come in, right? And this is where it starts to become incumbent on you to choose measures that have known psychometric or the psychometric properties of a test have been examined, right? And we get in this issue of subjectivity in measuring hypothetical constructs that aren't really hard and fast things, right? And so within our research, we generally just assume that we've got it close enough. But you may run into situations where that's an actual crucial part of your research question, and this assumption may make or break some inference you have. And so given the situation, that may be something that might be more important to think about than in other situations, right? Because we say in general, a 20 is lower than a 30, and a 40 is larger than a 30, and we assume on average that probably people who are reporting 20s are less happy than people who are reporting 40s, and we can generally make that assumption without too much influence or bias in our statistics. But I don't know, you may have a question where that does start to become important, or you're reviewing some research where sort of some inference hinges on the assumption that, oh, these are equal equal distances, right? So wanting to just be aware of some of these issues as you're going through, working through your own data and evaluating others. Other questions on this? Okay. Another thing I want you all to be aware of, anytime you transform, some people love to transform data. You'll hear me get on my soapbox about transforming data. Transforming data is not magical. We have to do it sometimes, but there are consequences to doing that, right? But technically, when we go through and we run a transform or analyses, any analysis on transform data is analysis of difference in sample medians, then adding, subtracting, multiplying, dividing, constant. Transformation is a non-linear calculation on individual scores. Transformation will change the shape of the distribution. This is why we do transformations, is to fix the distribution and or bend it to our will. And so although a transformation will change the shape of the distribution, it's not going to change the order of scores. Okay? So I apply a logarithmic transformation to my data. When do we often look to apply log transform to our data? What does log transform fix? Anybody know? Who's my alcohol researchers?
Me, but
Okay.
I don't remember.
Okay. Skewed data, right? Because what log transform does, it takes extreme values and brings them in, has a bigger impact on large values than it does on small values. So our log transforms, either base 10 or base E, generally use, and so one of our more common transforms is try and address bad skew in a data set, right? So I can log transform a number of drinks per day, right? And so most people are going to have, particularly if I am working with, say, high school students, most of them are going to be 0, right? And they're all going to be bunched up around there, but then we're going to have some people who are way out there. My log transform is going to bring in that tail, but it's not going to change the order in which people fall, right? It's not going to change the rank order of scores. So if I, in high school, drink 2 drinks a week, and Sam drinks 10 drinks a week, there's no transform that's going to make Sam's value be lower than my value. My value will always be lower than Sam's value. The distance between our values may differ depending on the transform, but he's always going to be ahead of me in terms of rank, right? So cases at the median of the untransformed variable are going to be remain at the median of the transformed variable. So, for example, here we've got audit. Audit is a measure of problematic drinking. Here are scores. We've got a clear skewed distribution here with sort of most people being on the low end, but we've got someone that looks like they're reporting pretty severe alcohol use and sort of this tail going out. And so what I want to do is I'm going to transform these data using the natural log transform. This is my log transform, or excuse me, this is my raw variable, this is my log transform. Was my transform successful? What do you think, Sam?
Yes, because you kind of got rid of the one all goods were right.
Yeah, my skew value for this is going to be a lot bigger than my skew value for this, right? And so for the purposes of my analyses in terms of bringing that tail in, it was successful, right? But you'll notice on the units, these have ceased to be meaningful units if I want to apply a real life interpretation to these audit units, right? I've gone from units of 0 to 40 to 0 to 4, right? And so now I'm interpreting this as the natural log transform of audit scores, which you get to say every time you talk about your variable if you've gone through and transformed it during responsible research, right? But what ends up happening is the median of this distribution is 3, right? People who had a score of 3 in my raw variable are still here at the median of, who has a calculator? See there, I told you guys I was going to have you do this. Alex, tell me what the natural log of 3 is.
Yeah, I don't even know what a log is, honestly. You probably do.
You just do log 3.
Yeah.
0.477.
Oh, no, the natural log of 3, not base 10 log. It's the ln.
It's just
Oh, it's the LN.
Yeah.
Oh, okay.
Oh.
It is 1/5 1.09.
1.09, okay, so 1.1. So the median, whoever's at the median, right? So Alex is at the median of the raw distribution, right? She has a value of 3, right? Her score, when we log transform, is still the median of the transform variable, so it doesn't change. The median doesn't, the people at the median, the value, the number changes, but the cases at the median of the distribution don't change when we log transform. And so then maybe we run a t-test looking at the sort of values here. Essentially what we're looking at is median scores as opposed to mean scores anytime we go through and transform. But important to consider that when we're going through and we have weird distributions that have skew, median is going to be our measure of central tendency that we want to look to, and then every time we're going through and creating transforms, we're working with good median-based statistics here. All right. So choose an index. When we want to choose mode, nominal scales, right? I can go through and assign numerical values to different brands of soda and can calculate an average on what people prefer. That's actually not anything that's meaningful, right? Anytime you see someone take the mean of something like ethnicity or something along those lines, it's nonsense, right? Measure of central tendency is going to be, of nominal scales is going to be the mode, right? Also helpful if we have discrete ordinal count level data, right? Because if we've got a variable where our meaningful interpretation relies on whole indivisible numbers, we may want to be looking to mode. We talked about number of children, right? We can't have 2/3 of the children, right? That's not a real thing. Same thing with rooms in a house. We'd say, oh, the average house has, 3.2 bedrooms. I don't know what 0.2 of a bedroom was. It's a very small bedroom, right? But in actual fact, that's not a real thing, right? So modal number of rooms in a home in this sample of homes is whatever it is. And then also helping to describe the shape of the distribution, using mode to supplement for mean and on a nice normal distribution, what are the mean, median, and mode going to be? The same, right? But as we start to get more interesting distributions like we work with in applied data, we can say here's the mean, modal value, however, was this, or medians and things like that. So again, wanting to use these, knowing sort of the strengths and limitations of each one of these, and be able to use this effectively as we're describing stuff that's going on in our data. To get measures of central tendency, if we go to analyze, then choose descriptive, statistics, frequencies, and then choose this statistics button up here. Will give us an opportunity to check mean, median, mode, and then we can hit continue. We can also get mean values in the future through analyze descriptive statistics, descriptives, to get our mean values. I just like to set up there, but multiple ways to get those values through SPSS. And we'll work on that when we get into actual real data sets. If we request through frequencies, this is the table we'll get. We'll have valid number of scores. Here looks like we've got a lot of missing scores, but of the valid scores that we have, here's the mean, the median, and mode. What does our data look like here for CAPS is an interview measure of PTSD, right? So what does the distribution, based on the mean, median, and the mode, what does our CAPS total scores at pre-test look like? What's that? What did you say, Angela? What's that?
They're high. But
They're high, but in terms of what do we might we infer or guess about the distribution based on this information? Close to normal, or at least to the extent that mean, median, mode are all kind of lined up fairly close to one another here, right? Starting to drift in terms of our distribution here. By the time we get to follow-up, this is going to be, say, 6 months post-treatment, right? our mean and our median are different, but our mode is sort of way off there, right? So we're starting to get something a little more funky in this distribution. Okay. So again, we want you all to be looking at the available data and start to sort of think about what does this say about the data, what does the distribution likely look like based on this information. So again, if I were to just give you the mean and median, like, oh, that looks pretty normal, but we've actually got our mode, our most common value is actually something quite a bit higher than this, right? Suggests to me maybe some sort of negative skew going on here. All right. Questions about measures of central tendency? Okay, cool. All right, so I'm going to move on, start talking about variability. If we're talking about variability in general, not variance, but variability. Variability referring to the extent to which our scores are spread out or clustered together, okay? If the scores of distribution are all the same, there's no variability. If scores in our distribution are all the same, what do we have? Do we have a variable? Nope. Rajiv, what do we have?
We don't have any variability.
We don't have any variability. What do we call that? If all the scores are the same. We have a constant, right? Not a variable, it's constant. All the scores in the sample are 7, right? Or all our people are female, right? So again, large differences between individual scores, large variability. If there's not, everybody's kind of close together, we have low variability. Okay? Our indices of variability describing distribution in terms of distance, right? In general, telling us how much distance to expect, depending on what type of metric we're talking about, either between any two scores or between individual score and the mean, right? Depending on what measure of variability that we're looking at. Also, I think this is important from a conceptual standpoint, variability is going to give us some sort of rough idea of how well an individual score that we would randomly select from the sample, right? Here's our sample scores. Pull one out, right? Without looking, and I have to guess how representative this score it is that I pull out, right? And I'm hoping that this score is representative of the whole sample. Am I hoping for, would I be rather, I've got 2 bins, right? I've got one bin has low variability, one bin that has high variability, and sort of some outcome that I'm wanting is depending on me selecting a score that's representative of the total bin. Do I want to be pulling from the bin with large variability or low variability? Low variability, right? I want to be pulling out of something where everybody's about the same, because what it's, this variability metric on each one of these bins telling me how much error to expect, right? In general, if I have to guess what the value is of the score that I'm going to pull out of this bin, what's my best guess? Probably if we're thinking in terms of central tendency. If you have to guess the value without knowing anything else, what's your best guess? Sample mean, right? Mean value, like you're probably going to be wrong, but you'll be less wrong than if you were to choose any other value, right? But if I have low variability in my set, the likelihood that I'm going to get something that's pretty close to the mean is a lot higher than if I'm pulling from a set that's got a lot of variability. Conceptually, if we're thinking about, and we'll get into this when we get in our mean-based statistics, this variability is telling us how much error to expect, right? If I go through and pull this random sample or this random case out of a larger bin, my measure of variability, and I say, all right, the value is 30, right? My measure of variability is telling me, on average, probably how close I'm going to be to the actual true mean value of whatever that sort of bin is. Okay, and so this is an incredibly important concept in understanding our inferential statistics. Questions about variability stuff in general? Okay. Indices of variability, at the most basic level, sort of pretty easy, straightforward. We're talking about range. Range is just the distance between the largest score and the smallest score in a distribution. We're taking the smallest score, highest score, we're going to calculate our metric of range. A couple different ways we can calculate range is the distance or the value between the highest and the lowest score, or the highest and the lowest score plus 1. People with nothing better to do with their time get pretty militant about which one of these is the correct way to calculate it. It doesn't matter. Asterisk here, this is SPSS calculates range as the highest minus the lowest. Textbooks sometimes, introductory stat textbooks will identify range as the highest minus the lowest score plus 1. I don't care which is one of the two, right? In general, range is a good thing to be aware of, but some limitations in terms of a measure of variability in that our range is determined solely by the two most extreme scores in the set, okay? Everything else gets ignored. We're just taking the lowest score, the highest score, calculating the difference, right? And so our range may not be terribly representative of our actual variability in the set. Our range, as a consequence, is going to be misleading if we've got distributions with very large or small scores. And so it's because it's not taking into account all values, often will provide an inaccurate measure of variability, particularly if we're working with a sample with extreme values. Okay. In general, Katie, how would you describe the variability in this set?
In general?
Yeah, pretty low, right? In general, we've got people scoring very tightly around our mean of 5 right here, right? And a nice clean distribution. Then we just got some joker out here at 20, right? Absent that person, we're looking pretty good, right? But our range is going to be massive. And so if you don't know anything else about this distribution aside from the range, you would say, oh, wow, we've got a lot of variability in these data, when in fact we actually don't. Okay. So range is nice, and I like when people provide range because it tells you what the highest score and what the lowest score is, right? For psychopathology types of stuff, clinical stuff, this is nice because it lets me know, like, how extreme are the people in your sample, right? If you're working like how severe is that range, if you give me the upper and lower limit, actually the range in and of itself doesn't tell you that. It's just nice to, a better way to represent range is just give people the lowest score and the highest score. If someone wants to calculate a range score, they can calculate that for themselves, right? But it is helpful to know sort of what the high end and what the low end is in terms of the distribution. Okay. Other types of range statistics. You all, first year clinical folks, aren't taking assessment with my lovely wife this first semester, but you will. Percentile will start to be a big piece of cognitive achievement tests and things along those lines. From the stuff that we do, you'll sometimes find people talking about variability in terms of percentiles and quartiles. Quartiles are the 3 points that separate a set of ordinal data into 4 equal sections. Okay, your first quartile, this is going to define the lowest 25% of your distribution. Your lowest quartile is going to be your 25th percentile. What's the interpretation of 25th percentile? Anybody with background in assessment stuff? Let's say you took a cognitive achievement test and scored in the 25th percentile. Is that a good thing or a bad thing? Okay, Angela, a bad thing? Why is that?
Below 75%.
Okay, you're quite a ways below 70.
Yeah.
It's basically saying that 25% of the sample has scored lower than me at or lower than my level, right? Which suggests that I performed worse than 75% of the rest of the people who've done this, right? Which isn't great, right? But if I'm in the 25th percentile of risk for heart disease, then that's probably a good thing, right? So again, percentiles being the percentage of individuals in the population scoring at or above, at or below sort of my score, right? So the second quartile, center of the distribution, median is going to be at the 50th percentile, right? This is the center. By definition, your median is calculated as the value at which 50% of the sample falls below, 50% above. Median is your second quartile. Third quartile, upper 25% of the distribution, talking about the 75th percentile here, we're saying that 75% of the sample of the population has scored at or below my score here. Okay. Interquartile range then identified as the difference between the first and the third quartiles. Right? If we take the first quartile, the third quartile, or the 25th percentile, 75th percentile, and take that, that's my range statistic that's identifying sort of the bound, not by definition, not regardless of the distribution, because we're working on median-based statistics, we're saying 50% of scores are falling between the first and the third quartiles here. Okay. Talk about that as the middle 50. So if we're looking at a normal distribution here, here's the median, the 50th percentile, the second quartile. Here's the first quartile, the third quartile, corresponding to the 25th and 75th percentiles. Your interquartile range, 50% of your scores, half of your scores are going to fall in that middle section here. 20 sort of above this tail, above the third quartile, you're going to have quarter of scores of the highest scoring scores. Below the first quartile, it's the quarter of lowest scoring scores here. This is scaled on a normal distribution, but this holds regardless of what the distribution looks like. Okay. So limitations of your interquartile range. We're getting rid of a lot of data, right? We're sort of cherry picking the middle 50% of that and ignoring the top 25%, the bottom 25%. We're leaving. You can have a horrible distribution and still have a pretty clean interquartile range, even if you have scores way down at the bottom or way up at the top. Okay? So this will start to become relevant to when we start talking about box and whisker plots, a nice way to graph distributions of data that aren't reliant on normal distributions using median-based statistics to take a look at where people are falling. You'll get plenty of practice interpreting box and whisker plots by the time we finish up with the year. So, any questions about this? Okay, cool. Let's take a break. Going to jump back in and talk about variability stuff. So, wanted to transition into variance and standard deviation. Okay, these are going to be the crucial concepts that we're going to continue to work through in any, for all of inferential statistics. Okay, variance, standard deviation are going to be our most common indices of variability. Once you guys have a good conceptual understanding of what these two metrics are, okay, standard deviation, loosely, not exact, but for all intents and purposes, interpreting standard deviation as an estimate of the average distance of any randomly selected score from the mean. Okay, so if I have my standard deviation of sort of some variable is 10, what that means, if I were to close my eyes and randomly select a score from that distribution, on average, I would expect this score to fall 10 units from the mean, right? If I had to guess, you can make me guess what this score is. Like I pull out a score and you say, what's this score? And I can't look at it. My best guess is going to be the mean, right? But I know probably I'm going to be wrong. But I'm going to be wrong probably on average about 10 units from the mean, right? And so, again, wanting you to be thinking clearly and giving a literal interpretation of standard deviation, okay? Variance, this is the second population moment from a mathematical standpoint. This is the second characteristic of the distribution we're talking about. The variance is the average squared distance from the mean, okay? And we'll go through and we'll take a look at this in terms of calculating these statistics here. Our variance is the variance is the big metric, probably the most important metric that we'll end up talking about as we continue to move forward. But variance in and of itself doesn't have a strong conceptual interpretation. I mean, conceptually, it's the average squared distance from the mean, but that doesn't mean a lot to us generally. If we take the square root of that, then we get the standard deviation, and we can say, this is the average distance of any randomly selected score from the mean. Variance in and of itself doesn't have a strong interpretive, much strong interpretive value for it. Stephanie, did you have, no. Katie, did you have a question? Okay, Sam, yeah.
I was gonna ask, why don't we just use absolute values?
Absolute values for what?
Or like, you know how we can have negative values if we add up and then take the average of that deviation. Yeah, the average of deviations without the square.
Oh, absolute deviations, yeah. There are some metrics for doing that, but they tend to work not as well at it or in all situations as squared deviations. So mathematically, there are some reasons in terms of theory and bias that make this a better approach than absolute deviations. But in some circumstances, there are cases where you can start deriving estimates of variability for absolute deviations. We're just not going to get into them here, okay? And again, if you were to select to use a metric like that, you probably want to have a strong rationale for why you're doing this aside from using the squared deviation method. Okay. So, direct relationship between variance and standard deviation. Variance is equal to the squared, take the standard deviation, square it, you get the variance. Take the variance, take the square root of that, you get the standard deviation, back and forth there. But what we see here is the calculation of variance, standard deviation, slightly different for our populations versus our samples. Okay? So, conceptually, standard deviation, cool kid in school, all right? Everybody likes standard deviation. You see standard deviation reported in your inferential statistics. Standard deviation is fine in terms of having some interpretive value. Variance, though, we want you to become comfortable with variance, want you to understand what variance is, and when we start to get older and mature, variance starts to become much more important, sophisticated, central to anything that we would go through and do. So what I don't want you to do is see variance and sort of overlook it and say, oh, that's scary and I don't know what it means. It's just the squared, average squared deviation. Standard deviation is nice, it's fun, it's easy to interpret, but variance is going to be the more important metric that we'll use as we move forward, and so on. You have a good foundational understanding of that. Okay. Any questions? Okay. So, calculating variance and standard deviation for the population. Okay. What we're going to do, we've got a set of 5 numbers here. Okay. And we have our 5 numbers, and this is our population. This is a population of 5, not a very big population, just 5 people in this population. Okay. Go through, list those out, and first thing we're going to do is we're going to calculate a deviation score for each value. Get used to the idea of deviation scores. This is a central component, things that we'll talk to and return to again and again and again and again. Okay, deviation score is just the difference between the observed value and the mean. In this case, our observed value, or excuse me, our mean value. What's our mean value for this distribution, Morgan? 6, right? So all we're doing is we're taking each one of these values and we're subtracting 6, because that's the mean. Okay? What we're then going to do is we're going to take the square of each one of these deviation scores. Okay? So take our deviation score, square that, going to get the column here, and then what we're going to do is we're going to sum the square deviations to obtain the sum of squares. So again, if you think back to your intro stat courses, probably talking about sums of squares. Sum of squares is just another metric of variability, okay? Sums of squares has even less interpretive meaning than variance, right? But again, it's the same thing, right? It's just a different language. It's a raw measure of variability in your scores, right? So we go through, create our deviation score, square that, sum up our squared deviation scores, gives us our sum of squared deviations from the mean. So if I ask you what's a sum of squares, think to yourself what sum of squares actually represents. Sum of squares The long form of sum of squares is sum of squared deviations from the mean. That in and of itself will tell you exactly what the sum of the squares is. So, jumping off of Sam's question, why do we worry about this whole squaring business? What does squaring things do for us?
Makes them all positive.
Makes them all positive. Why is that important? What's that?
And you said because math.
Because, yes, that's a good answer for most things because of math, right? What happens if we just square, what happens if we just sum the deviation scores? Yeah, we'll get 0. All the time?
When we have negative and
Yeah,
positive.
all the time, right? By definition, because of math, this column will always square to 0. If this column doesn't square to 0, you've miscalculated something, right? And so what we do is we square these. It creates a positive score, oops, and then we can calculate our sums. And so when Sam was asking about absolute deviations, what we could do is we could take the absolute value of each one of these and run some different statistics, but there ends up being biases in those where we don't get it in the square. Okay. So then what we do is once we got the sums of squares, we'll divide the sums of squares by the number of scores to obtain our population variance, right? And again, our variance, our metric of variance is for the population, literally the average of the squared deviations from the mean. Okay. And then what we can do is once we calculate our variance estimate, what we can do is we take the square root of the variance estimate to get our standard deviation. Again, at the population level, the standard deviation being literally the average distance of any randomly selected score from the mean. Okay. Computation formula, this is the conceptual formula. If you go through and think about this, you can literally see how we've gotten this statistic. What I want you guys to focus on is sort of understanding at a conceptual level what these statistics mean, because that's the level at which you'll need to understand these in order to problem solve your own stuff and figure out why things are way out of bounds or not way out of bounds, things along those lines. But this is a big table to calculate, to do this all by hand. Computational formula, mathematically, our x values, we're squaring those, adding those up, and subtracting the sum of the total of our x squares, squaring that sum, and then taking that divided by the number of squares of the population, okay, to get our sums of squares. Okay. Questions here? When you're using this computational formula, make sure that you're paying attention to order of operations, otherwise you get weird numbers. Okay. So, plausibility check. This is the thing I always want you, and this is sort of how you start to know whether or not people know what they're doing or just punching numbers, is when you get a number or some sort of statistic, and this is true for the entire year, what you should do is you should look at that statistic and say, does this make sense? Based on my understanding of what this statistic should be, does this seem like a real value, right? So let's say for these data set, mean of this population is 6, right? The average, the maximum distance of any score from the mean ranges between 1 and 5. Okay. So, given these parameters, what should my standard deviation be if my standard deviation is the average distance of a randomly selected score from the mean? Or what should it not be?
Bigger than 5?
Yeah, right? If I calculate my standard deviation is 6, I should think to myself, that doesn't seem right, right? So again, that Wilkinson article, okay? There's no substitute for common sense. Never assume that using a highly regarded program absolves you from the responsibility of judging whether your results are plausible, all right? This makes you look foolish if you start reporting figures that are clearly not reasonable figures, right? And in my mind, they're like this, when I'm reading your assignment, like this is what's going on here. This is the look I'm giving you in my head when you report a standard deviation of 100. I'm like, really? Okay, so again, just trying to emphasize that anytime you're doing this, like, you will make mistakes as you're running your analyses, Like, that no one is gonna do this perfect every time out of the box. I consistently make mistakes all the time. I'm not worried about you making mistakes. What I'm worried about is you understanding and being able to take a look and say, that looks weird. This doesn't sum to 0, and being able to go back through, catch when you've made a mistake, figure out that you have made a mistake, and then figure out where that mistake has occurred, fixing it moving forward. Okay? All right. Again, so if we're thinking about our goal of our inferential statistics, what we're trying to do always is take and draw some inference about a population from some sample that we've pulled out. Okay? And this assumption is based on, and this process is based on the assumption that our samples and the statistics we pulled from them are representative of the actual population. Problem is that samples consistently underestimate population variability, right? If I go through and I create, and I'm interested in average, or excuse me, variability in height among US adults, and I do a nationally representative sample, and I go through and I get 1,000 people and bring them in, and I calculate the variance of height based on the formula that we just went through, it will be systematically biased, right? And it will be systematically biased to the as a function of the size of our sample. Because what happens is extreme scores in our population probably aren't going to get captured, even if in our best sampling strategy. And what's going to happen is that's going to result in systematic bias, right? So again, here is my population variability. This is any normally distributed variable, height, weight, achievement scores, something along those lines, right? Even with my best sample, this is where I'm going to sample from, right? This is where I'm going to get my scores. But in actual fact, we have far more extremes in the population that I'm probably going to capture. And what this is going to end up resulting in is systematically smaller estimates of population variability than the true actual population parameter. Okay? So again, go back to the height example, right? Let's say I sample the height of 100 people, right? I'm probably going to get, maybe with 100 people, that's reasonably large sample for our perspective, right? Am I going to get some tall people, some short people? But I'm probably not going to get people who are under 4 foot or people who are over 7 foot, even though these are real values of the population in terms of height, right? I'm not going to capture those systematically in my sample, and as a consequence, will underestimate the variability of my sample. Okay. People see conceptually what's going on and why using our population formula, why our, if we're calculating variance based on a sample, why we're going to systematically underestimate variability in the population. Does it make some sense? Okay. So what we have on our hands then, if we're calculating variance using the population formula, if we apply that to a sample, what we have is a biased sample statistic. Sample statistic is going to be biased, and you'll see this a lot, right? Particularly if you start to get into more sophisticated methodological literature, you'll see things referred to, this is a biased parameter, or this statistic is biased. What that means is that if we take the average value of a statistic calculated over numerous replications, that statistic systematically overestimates or underestimates corresponding population parameter. Sample statistic is unbiased if the average value over a number of replications is equal to the population parameter. Okay, the mean is an unbiased sample statistic. Doesn't matter if we're working with populations or samples, the mean is unbiased, right? Because on average, we're getting these people, right? So we're missing people on the high end, but we're also missing people on the low end. And so calculating the mean is the arithmetic average of the scores in our sample. It's not going to be perfect because of why? What do we call it when our sample statistic doesn't equal the population parameter? Sampling error, right? That's all it is, right? And it's going to happen all the time, right? But on the aggregate, as we collect multiple samples of 100, of 100, of 100, and take the mean of all those samples of height, we're gonna get an unbiased estimate of population parameter. Variance isn't the case, right? If we sample and resample and sample and resample, we're still getting all these people, we're systematically excluding people on the extremes. And so if we use the population formula to sample with our samples to calculate variance, the average of those variance estimates is always going to be lower than the actual population variance. And so this is a problem. Fortunately, we can correct this bias with slight modification of the formula. What we're going to do is we're going to take our sample variance and estimate our sample variance by taking our sums of squares and dividing it by the number of people in our sample minus 1. How is this going to systematically correct for underestimating population variance? Sam? So our population formula just has the sum squared divided by the number of observations. How does our sample formula correct for the underestimation of sample variance?
Is it because you can't get like exact size of the population?
Right. So we're just taking the number of people in our sample and not dividing by the number of people in our sample. We're dividing our sums of squares by the number of people in our sample minus 1. What's that going to do to our estimate here?
Increase.
Why?
Because you are lowering the denominator.
Exactly, right? We're dividing this sums of squares by a smaller number. Another big thing we want you to, we'll hit this over and over and over again, sort of recognizing what happens with ratios, right? If I take, all things being equal, if I take this number and divide it by a smaller number, what am I going to get? A larger outcome, right? Or divide this by a larger number, what's that going to do to my output? Make it smaller, right? And so what happens, and people smarter than me have gone through and figured this out, and this provides this small correction, taking this sample size, subtracting 1, and I can't tell you why 1 is the number because of math. This provides an unbiased estimate of the population variance. Okay. So what's the biggest thing that starts to impact the adjustment we're making from the population formula to the sample formula? Yeah.
We're increasing the variance.
We're increasing the variance, right? So we know that if we use the population formula, we're going to systematically underestimate. So if we divide that by a smaller number, it's going to sort of boost that up, make an upward adjustment, right? What's the magnitude of that upward adjustment based on? Looking at the formula here. Yeah, the size of the sample. Why?
Because that's the number of the sample minus 1.
Right. And so where am I going to get a bigger adjustment to my to the estimate of my population variance? Stephanie, if I have big samples or if I have small samples?
Where, can you repeat the question?
Yeah. What's going to give me a bigger adjustment to my estimate of the population variance if I'm using this formula with big samples or small samples?
Oh, with small samples.
Why is that?
I blanked, but I knew the answer at first. Yeah, because I can't explain it mathematically, but the difference between like dividing by 99 versus dividing by 100 is not as impactful as dividing between 3 or 2.
Yeah, right. If I have a sample of 10, right, and I subtract 1 and divide whatever this number is by 9, all things being equal, that's going to create a much larger adjustment than if I have a large sample. And this makes sense, right? Because if I've got a small sample, in theory, I'm probably just capturing people right around here, right? And so probably what I've done with a small sample, I've made a larger underestimate of the true population variance, right? If I grab a sample of 6 people I'm not gonna get people even probably slightly larger or slightly smaller, right? It's probably gonna end up being people right there in the center of the distribution. As I start to get larger and larger samples, I'm more and more likely to catch those people who are on the boundaries, right? And so with a larger sample, my samples become increasingly more precise, still systematically underestimating, but by less than if I have a small sample, right? And so again, if our large sample, my adjustment relative to the population formula is gonna be pretty small. With small samples, my adjustment's gonna be quite large. Again, wanting to emphasize the importance as we're moving forward with things, being able to sort of look at these ratios and saying, what happens if my denominator is smaller or larger? What happens if my numerator is smaller or larger? What does this do to my outcome? And using this to try and help develop a strong conceptual formulation of what's going on with some of these statistics, okay? So people see, one, why we have problems with, if we were to just calculate variance in our samples using population statistics, why that's gonna result in a systematically smaller estimator of the population variance, and then two, how this correction starts to have an impact. It's always gonna make your sample variant, your calculation or your estimate of the population variance larger, but the extent to which it makes it larger is gonna differ very directly as a function of the size of your sample. People comfortable with this? Okay, cool. So, calculating variance and standard deviation, if we're don't have access to the population, if we only have access to the sample. Same thing, we got our scores. This time we don't have a population of 5 scores, we have a sample of 5 scores. Right? We're gonna calculate a deviation score. We're gonna square the deviation score. We're gonna sum up our squared deviations. To this point, we've made no changes. It's the exact same as if we were calculating this population parameter. But now for our sample variance, what we're gonna do is we're gonna take this sum of squares and we're gonna divide this by the number of observations in our sample minus 1. And then we're gonna take the square root of our sample variance to get our sample standard deviation. But the computational formula for your sum of squares is the same. Everything identical up to this point. The only adjustment, the only difference that we make in calculating population variance versus sample variance is this adjustment to the denominator here. Cool? All right. So just as a summary, right? In the example that we've given here, here's population sum of squares, sample sum of squares. These are identical because calculation of sum of squares is the same, right? Variance though, in our population, if we take these scores that we had and we say this is all the scores in the population, we get a variance estimate of 8. But if we say that these are 5 scores from a much larger population, we see this adjustment creates an upward, it makes an upward adjustment on our variance estimate, right, to account for systematic bias, particularly in a sample of 5, right? Dividing our sums of scores of 40 by 4 instead of 5 makes a noticeable adjustment into that variance estimate, right? And then a standard deviation, taken as the square root of both of these, ends up with, if we were to calculate standard deviation using the population formula, gives us a smaller estimate than if we're using our sample estimate. But in general, this is what we're going to be using because we're never going to be using population values. Okay, and then formula stuff. Questions on this? Alex, what's the literal interpretation of standard deviation?
Average distance between
Close, yeah. So,
close-ish?
yeah, right. So the average distance we would expect from a randomly selected scoring distribution from the mean. Right? Okay. So again, variance and standard deviation tends to be people have pretty strong on the mean, right? Variability and variance is something that people sometimes have a more difficult time with. Want to make sure, but it just ends up being crucial to applied analyses. Something we want you guys to have a strong handle on as we move forward. Okay. Questions on any of this? Cool. All right. Utility or standard deviation. describes variability, measuring typical distance from the mean, okay? In distributions, sometimes we'll have individuals that will be close to mean, sometimes we'll have individuals be farther from the mean. If you're reporting the means and standard deviations, and you should always report the means and standard deviations for, like, write that in giant letters, right? In any research that you do, always, always, always report means and standard deviations. In general, we'll talk about this and you'll read about this in our readings. You should probably be reporting a lot more than just the means and standard deviations, but at bare minimum, means and standard deviations, because what you give me, if I know these two things, I have information about the general distribution of scores. I know based on standard deviation, if I were to randomly select a score, on average, how far it's going to differ from the mean, and it's going to start to facilitate inference about individual scores. This is a big thing, again, in clinical work. Just an FYI for all you experimental folks. What I'll often see if I'm in supervision is someone will say, okay, I gave someone a score on the social anxiety measure and they scored a 30. Does that tell me anything if I'm not familiar with this scale? No, that's a number. I don't know, it could be a billion, doesn't make any difference to me. I have no way of knowing that. What if they say, so this person scored a score of 30, and the score from a clinical sample of individuals with social phobia is 40. Do I have more information? I've got more information, right? It looks like this person is scoring below the mean on social anxiety relative to some reference group of individuals with social anxiety. But what's the problem? Yeah, I don't know, right? So maybe scores in that sample of individuals with social phobia, maybe everybody scored like right around that 40 mark, or maybe they're all over the place, right? I have no way to judge. I mean, I have some information, but I have no way to determine whether or not the score that I got from my person is typical or atypical of individuals with social anxiety, right? But if I get the mean and standard deviation of that reference group, I can start to get a better sense of where this person falls relative to some type of reference point, okay? And so if I'm looking at standard deviations in general, if I'm talking about some sort of distribution with a normal, reasonably 5% of score, or excuse me, 68% of scores, about 2/3 of scores are going to fall somewhere between a standard deviation above and below the mean. If I go out just 2 standard deviations, I'm expecting 95% of the distribution or the population to fall somewhere between 2 standard deviations, and over 99% to fall within 3 standard deviations, right? So by knowing the mean and standard deviation of some normative group, I can start to tell you, or may start to make inferences on relative position of your scores relative to some other reference group, okay? Again, assuming something that, if we're talking about some construct that assumes some reasonably normal distribution. Okay? So you guys, I don't need to necessarily memorize this, but just in terms of thinking about where things fall, okay? So what we can start to do is I can say height of average adult male is 5'10" with a standard deviation of 3 inches around that mean, okay? And so, well, you can see we've got David, John, and Matthew. Are these scores extreme? What do we think? Katie? What about David? Is David having an extreme score?
It's outside of one standard deviation.
A little more than 1 standard deviation, but not much, right?
Fairly average.
So fairly average. All right. What about John?
He's more extreme.
Yeah. John is about close to 2 3/4 of a standard deviation above the mean, right? So we're starting to get more extreme here. What about Matt? Matt's 5'2". It's 2 standard deviations below the mean, right? And so if we're thinking about height on a normal distribution, right, that's actually fairly farther below average than what we would expect based on the mean, right? So we're 95% at 2, so we would expect math to probably be shorter than, there's 2.5% of the population is gonna be shorter, as short or shorter than Matt relative to other people. And that starts to give us a sense for sort of the level at which these scores are extreme or not extreme, right? Same thing, we've got a measure of extroversion scores, mean of 85, standard deviation of 20. Bert, score 120, is that extreme? Under 2, right? So again, probably what we would expect, reasonably not atypical. Leon, here's about 2 standard deviations above the mean, right? So that's a little more higher. Third person, about a standard deviation and a half below the mean, so low but not sort of wildly low, right? So what we can do is we can start to use information about the mean and the variability of scores around the mean of the population, start making inferences and start to gauge the extent to which scores are large, not large, so on and so forth. People see what we did and how we calculated all that. We'll just spend more of this, more time talking about this in the next lecture, calculating z-scores and stuff like that. Okay. So with our standard deviation inferential statistics, again, what we want to do with our inferential statistics is start to take a look and be able to detect meaningful patterns of relationships. Basically what we're looking at, we'll talk about this as we, next semester, we're looking at associations, right? Is group status associated with some outcome? Most of the stuff that we're going to be doing this semester is saying, do we see mean differences in this group versus that group? But the question is if I see a difference in these two groups, the question is the difference we see between these two groups, is this a function of actual differences in the respective populations, or is this just random fluctuations in data, right? So I've got two populations, population A, population B, right? And I go through and I pull a sample from population, and population A and population B have the exact same mean on whatever it is I'm looking at. Mean of the population is identical in population A and population B, but I pull a sample from population A and I get an average of 30, and I pull a sample from population B and I get a sample of 30, an average mean score of 35. What have I got here? Sampling error, right? And so my question is the differences that I see, do they exceed what I would expect just based on random fluctuations, right? And so what we can see when we've got data with low variability, right? If we've got scores that are very, very tight in terms of their variability, it's easier to see what look like systematic differences in cases with low variability, whereas when we have data with much larger variability, harder to see whether or not we have a difference here. Okay. So for example, if we've got 2 experiments. In experiment A, we've got scores for group 1, we've got scores for group 2. Experiment B, we've got group A, and we've got group B. Which one of these sets, experiment A or experiment B, are we seeing more variability in our scores? What's that?
B.
More variability? Yeah. And how did you identify that, Sam?
Because there's more distance between the numbers, any 2 numbers to choose.
Within a group, right? So if we look at group 1 and group 2 in experiment A, these are all pretty tightly clustered around. Like there's not a lot of jumping around here. If we look same thing in group 2, we're not getting much jumping around. Group A here, boy, we've got anywhere from 15 to 57, 21 to 61, right? If I look at both of these, means for both of these, mean for group 1 and group A is 35. Mean for group 2 and group B is 40. But which one of these is going to give us, which one of these sets do we see get a better sense of whether or not we have systematic differences between the 2 groups? A, again, yeah, why A, so.
Because there's less potential error.
Right, right.
Because differences are not due to the individual scores.
Well, yeah. But again, remember our measure of variability conceptually it tells us how much error we would expect in any randomly selected score. If we say the mean of this is 35, our average distance from 35 is actually quite small here. And if this is 40, average distance of here is quite small. If I randomly select any member of this group or any member of this group, they're pretty representative of the group as a whole. Versus here, well, I could randomly select a person who's 15 and I'm still 15 points off of the mean, right? That's not a great estimator. Same thing here. If we look at this graphically, right? So we've got group A, this is low variability. We see the mean of group A, or the mean of group 1, the mean of group 2. If we look at distribution of scores here, very little overlap, right? We've got kind of two very clean distributions that are clearly separate. In this case, even with only 5 scores or 4 scores, we're probably going to, I don't know if we're going to get evidence of statistical reliability, but it looks like we're working with 2 different populations here, right? Versus experiment B, that's an ugly distribution, right? If we go through and we take a look at the distributions are different for these samples, right? Or the projected population distributions are different, but they're not different by a whole lot, right? And so we've got a lot of variability, more variability in experiment B that's starting to obscure whether or not we're having systematic differences or if the differences we're seeing in this sample are more attributable to just random noise. Okay? So which one of these are we more likely to get a statistically reliable? So we're running a t-test. What's that? A, right? This is what you want your thesis data to look like. This suggests that you've done a good job, barring fabrication of data, that you've done a good job of measurement and a good job of selecting. All your RAs are on task. No one's gone rogue and doing their own thing in terms of collecting your data, right? This is maybe more often what happens. Is applied statistics and research is a sad business, but if you get enough people, right, you might be able to detect the difference here, but you just got a lot more error to deal with and a lot more noise to push through in order to try and detect that reliable difference. Okay. People getting a sense, sort of understanding what's going on with some of this stuff. Any questions? All right. Okay, characteristic standard deviation. Adding, subtracting the constant from every score and distribution doesn't change the standard deviation, right? If I have a sample of 100 people and my mean is 50, and I add a value of 10 to every score in the distribution, Rajiv, what's my new mean?
Sorry, what was the question?
If my mean was 50 and I add a value of 10 to every score in the distribution, 100 people, what's my new mean?
It's the same.
If I add 10 to every score in the distribution and my mean is 50, what's my new mean of that?
60.
60, right? So if I go through and I add a constant to every score, it's going to adjust my mean by whatever sort of the constant was, right? But what's my, so again, sample mean was 50, but I go through and add a constant of 10 to every score in the distribution, and say I have mean 50, standard deviation of 10. I go through, add a value of 10 to every score in the distribution. What's my new standard deviation?
It doesn't change.
It's still 10, right? Because the spread of scores doesn't change. I've just shifted that along the distribution, right? But if I divide each score in the distribution by a constant, my standard deviation will change by that same constant, okay? So again, Rajiv, I've got a sample of 100 scores, mean of 50, standard deviation of 10, and I divide every score in the distribution by 10, what's my new standard deviation?
So mean is 50, standard deviation is
Well, mean isn't 50, mean is now what?
100.
What's the mean of the new distribution? If I take every score and divide it by, it was 50, I take every score divided by 10. What's my new mean?
It's going to be 5.
5. And what's my new standard deviation going to be? It was 10, I divide every score by 10. What's my new standard deviation?
Just 10 divided by 10. So you are asking standard deviation, right?
Yep.
So it's one.
One, right? So, again, adding, subtracting a constant doesn't change the standard deviation. Standard deviation stays the same. The mean will change, standard deviation won't change. But if I multiply or divide by a constant, right, what's gonna happen is my standard deviation now will change by the same constant. Again, shape won't change. Shape will be identical. It's just my metric is gonna change around, okay? Factors that start to influence my variability in general. It doesn't matter if we're talking about mean, variance, standard deviation, range, interquartile range types of things. Things that are just going to start to impact my measures of variability. Extreme scores, okay? Range, variance, standard deviation. Extreme values, if I start throwing extreme values way out on the edges, it's going to start changing things, right? It's going to impact the range more than, on average, than the standard deviation and the variance, but extreme values are going to start to change those. Sample size, okay? Range is increases with sample size. Variance, standard deviation is going to remain relatively unaffected. Why is this? Any ideas, Morgan?
No, I'm confusing myself, I think.
As my sample gets larger, my range is going to get larger, but my variance and my standard deviation are going to remain pretty much the same. My variance and my standard deviation will remain fairly stable, regardless of increase in sample size.
No, I'm just confused as to why the range would increase if the sample size increased, because what if we had some of the same values?
So on average, all things being held equal, right? If I have let's say I've got a good random sample, as my sample size increases, my range is going to increase. Why is this? Anybody help her out?
Is it because?
Oh, go ahead. Kitty.
Because we're more likely to have extreme.
Yeah, right. I'm giving myself more opportunities to randomly pick people out from the ends, right? So as my sample starts to get larger, right, it's more likely that I'm going to capture 7-footers and 4-footers in my sample of height, right? Because I'm just having more opportunities to grab that golden ticket there out on the edges, right? But my variance and my standard deviation aren't going to change a whole lot. They're going to remain relatively stable because one, for smaller samples, I'm going to already have an upward adjustment for both of those anyway. It's going to be larger for my smaller samples. And then as I start to get quite large and start to capture those big samples, those outlying values that I capture that would normally bring those out are going to be offset by the larger number of people who are being pulled from the middle. And so my variance and my standard deviation are going to remain relatively stable across sample size, but my range is going to start to get bigger and bigger as my sample size increases, all things being held equal. Okay. Stability. Range fluctuates unpredictably across samples. If I have multiple replications, who knows, my range may vary by a great deal, right? So this one, I've got a range of 10, but this one I actually accidentally had a basketball player come through my study, and now I look at my range is massive, right? And it's just going to be really unstable, jumps around. Again, variance and standard deviation remain relatively stable. And then open-ended distributions are censored variables. We can't calculate range, standard deviation, or variance in censored data, because in order to calculate all of these, we need to know what the actual value was, right? Not just everybody came in and we capped them out at 100 and then left it at that, right? And so that starts to become problematic for calculating censored data. Questions on these factors? Start to make sense conceptually? Okay, because this is a harder, like oftentimes these end up being kind of abstract things, right? Like in your undergrad statistics class, it's probably just like, oh, this is standard deviation, and now we're going to move on, right? We want you to understand conceptually what's going on with this and how characteristics of your data is going to systematically impact this, again, so you can have a good understanding of your own data, your own research, and then being able to evaluate other people's research and how your study relates to other people, so on and so forth. Measures of variability in SPSS. We go grab analyze descriptive statistics, frequencies, statistics. We can grab quartiles here, standard deviation, variance, range, all through there. This is what your output might look like. So we've got, again, for 3 different variables, measures of standard deviation, variance, range, and then our percentiles are 25th, 50th, 75th percentiles here, right? And we can see across here are, and you can see our variance. It's hard to put a reasonable interpretation on that because those just end up being big numbers and sort of abstract. But if we look at our standard deviation, we say on average, scores are falling about 17 points from the mean when people are coming in for treatment. By the time we finish up treatment, our variability around the mean started to get quite a bit larger, right? Why is that? Treatment works for some people, not for others, right? Everybody's coming in pretty miserable. By the time they leave, some people are better, some people are not. We tend to see an increase in variability by the time we hit the end of treatment. But range, smaller here, larger here, and then where people are in terms of percentiles. Looking at our percentiles, does it look like treatment had some sort of effect? Right? We got a drop in median values, right? 50th percentile is our median, so our median, our middle score in this distribution drops down quite a bit, right? So that's good. And so our quartiles, so we're looking at this, you know, we don't have mean values, but it looks like we're getting, although our variability is increasing across assessment points, looks like probably we can infer that things probably had a drop in terms of at least median values in that middle score across the first, second, third assessments here. People seeing that, comfortable with that? Cool. All right. One thing, don't report statistics greater precision supported by your data simply because they're printed that way in the program. What are we talking about here? What do you think, Sam?
Possibility for error.
Yeah, possibility for error. Depending on how you have your variables set up in SPSS, it may, if you have it running measures out to 4 decimals, like we do here, right? These are whole, we're collecting these scores in whole numbers. 4 decimals is way too, we don't need to carry things out to 4 decimals, but you see this sometimes people are reporting means out to, you know, 6 decimals just because the computer program gave them an appropriate number of decimal places to drop things out through, you know. 2, maybe 3, just don't go through and write out. People write out p-values to 7 decimal places, don't do that. So again, thinking about your level of measurement and what makes sense in terms of how many decimal places. I mean, starts to relate into science and significant figures, right? We're not as strict, we play a little more fast and loose in terms of statistical stuff, but whole numbers, probably too coarse. 7 decimal places, probably too much. Making us an evaluation on that based on your data. Okay. Questions? Awesome. All right. We did great time. You guys are fantastic. Plugging through this. I'm going to talk about distribution shapes here. Okay. Symmetrical normal distribution. Again, this is a nice theoretical distribution of achievement, right? Is tested to your IQ score. If we've got a nice symmetrical bell curve, mean, median, mode, all fall in the same value. Everything's right in the world. We're very excited. This is what we're hoping for and never achieve in terms of our actual applied data. We can also, though, have symmetrical data that are non-normal. Symmetrical data, we can take that on the mean, median, mode, fold it in half, we get the same distribution on either side, right? We can have this in non-normal data if we have bimodal, trimodal, different distributions. We can take it, we can fold it, it's still symmetrical, but we've got multiple modes, even though the mean and the median fall in the same spot, right? So here, the mean and the median actually aren't a very good measure of central tendency, right? Because it's actually pointing to a value that's not actually common. In the trimodal distribution, you might make an argument that this is maybe still your best bet in terms of measure, central tendency, but things start to get a little bit tricky here. But in terms of what we're going to do again and again and again and again, is I'm going to have you go through your screen data and tell me what the distribution looks like. This is giving you language to start talking about what the distribution of scores look like. It looks normal, symmetrical, or it looks symmetrical, or the bimodal, right? You can get symmetrical and non-normal, right? This is a nice box-shaped distribution where we've got equal representation of the 5 scores in this distribution. And again, mean and median is still a good measure of central tendency, but it's certainly not a normal distribution here. Then we have skew. Skew is our third population moment. This is the third characteristic mathematically that we use to describe shape of distribution. Describes the symmetry of the distribution of scores. Positive skew, tail extending towards higher values. Negative skew, tail headed pushing out towards the lower negative values. Mean, no longer a valid index, right? If we've got a skewed distribution. Our mean will always be farthest toward the tail. Our mode will be to the far right or left. Median falling right in the center. Well, not right in the center, but sort of somewhere in between those two when we're talking about a skewed distribution. The extent to which these are all spread apart depends on the extent of the skew. People familiar with skew in general thing? Okay. Fourth population moment is going to be our kurtosis. Okay. Kurtosis, people sometimes have a hard time conceptualizing kurtosis. This fourth population moment describes the shoulders and the peak of a distribution. Okay. So if we're talking about positive kurtosis, this is the leptokurtic distribution. Leptokurtic distribution has heavier tails with a narrow peak. Okay. So this is sort of approximation of a normal distribution here on the dotted line. Our leptokurtic, or our distribution with positive kurtosis, has a thin peak that kind of sticks up, and then it comes down pretty steep, and we end up with thick tails that continue out, whereas our nice normal distribution kind of centers down asymptotically to 0. Okay. By contrast, our negative kurtosis, our platykurtic distribution, this is our normal curve. Negative kurtosis indicates kind of a domed, humped shaped, right? We've got kind of a flat center of the distribution that then kind of just comes down into sort of a kind of a boxy kind of dome shaped here. So we would say flattened center and heavy shoulders versus narrow peaks and wider tails with positive kurtosis. Okay. Kurtotic distributions underestimate population variance. Okay. Doesn't matter if we've got positive kurtosis or negative kurtosis, both tend to systematically underestimate the actual population variance. Why is this? Makes sense, right? So why does negative kurtosis underestimate population variance?
It excludes the extreme values.
We're not getting the extremes, right? We're kind of missing the stuff, right? We're not getting these folks, and so we're sort of systematically underrepresenting population variance. What about this? Why are we systematically, with a positive kurtotic distribution, how are we underestimating population variance with positive kurtosis? Yeah.
Because we are overestimating the number of people who are scoring within that mean.
Yeah, right. We've got too many people sort of right here along this mean, right? We're missing all of this. We're catching the tails, right? But we're missing sort of all this within sort of the shoulders. Our shoulders are too narrow, and so this group of people who we should be getting who are farther out, we're underrepresenting. So kurtotic distributions, always underestimating population variance. Impacts our quality variance tests that we'll go through and talk about with our mean-based stuff, and can start to, in certain cases, introduce bias into our parameter estimates, standard errors, and things along those lines. Kurtosis ends up being, as we get into the regression-based stuff, something that we want to take note of, particularly in smaller samples. So, people have got a conceptual picture of skew kurtosis. Skew's easy, kurtosis, people got that? Okay. It's a wonderfully kurtotic distribution. Why is this kurtotic? What do you think? Lauren?
Oh.
Why is this kurtotic?
Sorry, I was looking at
No,
it.
no, okay.
They're all the same.
Yeah, it's boxy, right? It's just a straight up box, right? There's no peak, there's no, it's just, and is this, what type of kurtosis do we have here? Positive or negative? Yeah, Lauren, yeah.
I don't know.
What is it? Good. Alex, did you say?
Is it negative?
Negative, why is it negative? Yes.
Because it has a flattened center?
It does have a very flattened center and sort of boxy square shoulders, right? So this is your negative kurtosis, okay? Statistical indices of skew and kurtosis. We can go through, put formal tests and start to provide an actual numerical metric to help us gauge the extent to which our distributions are deviating from what we would assume under a normal distribution, okay? We have formal tests of these, okay? So you can test whether or not you have a significant level of skew and a significant level of kurtosis. These are useless and you should never use them, okay? What ends up happening is we start talking about inferential statistics. What ends up happening if you've got large samples that you should have if you're running data, what ends up happening is these tests are overly sensitive, right? And what they'll say is you have significant skew, and then you send a paper to me where you've gone through and run a bunch of nonsense transformations because you have significant skew. When your skew is fine, it's just not normal, or not perfectly normal. But the assumptions of our tests aren't that our distributions are perfectly normal, and so you've made things way more complicated than you need to be, right? But what we'll do is evaluate the shape of our distribution more in terms of the absolute values of our skew and kurtosis. In general, if we've got skew and kurtosis less than 2, you sort of, it's approximating normality, kind of, right? If we start to get skew values of greater than 2 and kurtosis greater than 8, or less than 2 and kurtosis less than 8, we can start to talk about this as approximating normality with sufficiently large samples. But this is kind of pushing things a little bit, right? What we find is that as our samples start to get larger and larger, impact of skew and kurtosis start to decrease. So positive kurtosis, negligible, within reason at samples of over 100. Negative kurtosis, negligible at samples over 200, right? And so as our samples start to get larger and larger, starts to become increasingly robust to some of these types of violations. But what we're going to do is we jump into screenings, not just sort of taking a look at some of these values and trying to make a determination on the extent to which these data are non-normal, and then trying to make a determination whether or not this is going to be problematic for our analyses or not problematic. Okay. Getting skew and kurtosis in our SPSS program, analyze descriptives, and go through and grab options and skew and kurtosis. You'll do this a lot, so but just as a preview of where that's at. Our skew and kurtosis values and our output. So here, again, this is this CAPS data that we've been working at. Katie, tell me, do I have problems, do I have concerns with skew and kurtosis for my 3 assessments of PTSD in this sample? So here are my skew values and here are my kurtosis values.
kurtosis levels are pretty
Kurtosis is getting a little bit above, but we're still well under 2, right? So probably not anything, at least from a statistical standpoint, that I'd be concerned about from a perspective of analyses, right? What about skew and kurtosis values for these amusement ratings that I've collected? Or excuse me, these emotion ratings that I've collected.
It's well above 2.
Yeah, no, these are bonkers, right? This should cause me to have a great deal of pause, right? But if we think about what I actually did with this was I showed people a film that was objectively rated to be amusing, and then asked them the extent to which they experienced amusement, and that looks pretty good, right? If I asked them how much they experienced anger, all of a sudden we're skipping. I've done the weird thing, right? I've shown you something that's funny and asking you how angry it made you. And it looks like it doesn't make people too angry at all, but at least we've got a couple of people who are reporting, at least at a value of 2, angry, and that's starting to cause some positive skew and some kurtosis. If I ask you how fearful that made you, I basically collected a dichotomous indicator, right? So we've got a kurtosis value of 96, that's not good, right? And so wanting to go through and take a look at these indices to start to make a determination on whether or not this is something we should be looking at before moving forward with our data. Okay? So, last thing we're going to talk about here, outliers. Okay? Univariate outliers, extreme values. Okay? What we identify as an outlier is going to depend on the situation, sort of your personal feelings at the time, a lot of different things, right? But in general, conceptually, we're talking about some value that is considerably larger than the rest, is likely to maybe disconnected from the rest of the distribution, things along those lines. Possible causes, anytime you identify an outlier, go through and check first thing of all to make sure that there's not an incorrect data entry, right? Someone hit 5.5 instead of 5, that's going to register as an outlier. Go through and check and make sure that things were entered correctly. Failure to specify missing data code. In SPSS, something that I do in my lab, because we have research assistants entering data, if someone has not completed an item on a questionnaire, I don't want them to just leave it blank, because then if I'm looking at the data, I don't know whether or not the person actually, the participant actually left that blank, or someone forgot to enter it. And so what I have them do for missing data is enter a code that's clearly not a valid code, but it's a 999. I can tell SPSS to ignore 999 because that indicates missing data code. But sometimes I forget to tell SPSS that 999 indicates missing data, and they'll say I've got a terribly skewed distribution because I've got 3 people who scored 999. And so we'll need to go through and make sure that that's not an issue. Wanting to know whether or not the case is not an intended population of study, right? I want to look at income in undergraduates, right? And so I've gathered income in undergraduates, and it tends to be quite small. But I've got someone who's reporting an income of, $85,000 a year, and that's an outlier. And I'm like, what's going on? I go through and look like, oh, it's a non-traditional student who's just in the class. They're in their 50s. They're professional. They're just taking this for their own enrichment. This person is not a member of the intended population. My intended population is undergraduates, 18 to 20, right? This person is not a traditional student, so I'm going to go ahead and get rid of that outlier. That's an outlier, and but it's not. That person isn't representative of the population I'm trying to target, right? Or maybe the case is a member of the intended population, but my sample is underestimated. Again, I'm interested in looking at the relation of nutrition across different countries, and so I'm looking at undergraduates in different countries, and but I've got limited resources, and so I'm getting samples of 20, and I catch a basketball player in my sample. That person's height is representative because they're an undergraduate at the university, but in my samples of 20, I've systematically underestimated my assessment of height, but I just happen to catch So I hit the jackpot and hit someone who was 7 foot, but now they're throwing things way off base, right? So this is a more difficult situation where I have to make a determination, do I keep this person, do I not keep this person, do I do something else with the data, and we'll talk about some of those options, right? Potential consequences of outliers starts to impact our coefficients, right? Particularly means starts to drag things out in small samples. Can happen, if they're very extreme, can start to impact my variance and standard deviation estimates. Causes inflation in both type 1 and type 2 error. Starts to screw up the generalizability of my solution. I'm getting effects that I can't reasonably apply to the actual population because I've got weirdness in my data. So outliers are bad. Want to make sure that we're going through and addressing those if they start to pop up in our data. Right. Thinking about outliers, we can have outliers in categorical data, and this is important to think about. Okay, we tend to think about outliers occurring in our continuous scores, things like income or whatever else it is that we're taking a look at. But for our categorical data, we can start to see outliers here. Categorical outliers in the dichotomous variable, we're going to see these in data where we have very unequal splits, right? On a ratio of 9 to 1, right? So I'm interested in looking at gender in my sample, or gender in my sample here, but 90.5% of my sample is women, only a very small set is males. That's males are an outlier, right? We go there, a huge unequal split. Same thing with ethnicity. If 93% of my sample identifies as white, non-Hispanic, and racial ethnic minorities make up 6.7%, one is a bad variable just because we are comparing people who are white, non-Hispanic to everyone else, which is problematic for conceptual reasons. For statistical reasons, I've got a huge discrepancy in the sample here. What's going to happen is that people in the smallest sample, or on the smallest category, they're going to have an undue impact on effects, right? The people, so if there's only 5 of us, it's like Wyoming and the Electoral College, way outweighed in terms of, over the Senate, right, in terms of our power relative to the number of people that we have here. And so we can start to have an undue influence. Starts to, whereas maybe here normally we would have a strong relation between gender and some outcome, but if I've got this huge undue split, that relation might start to look smaller than it would in the population, just because I've grossly oversampled women in my sample here. And splits that I have in my categorical variables, I should probably make a strong determination on whether or not this is a central thing or just something I want to include just as a covariate. And if it's not central, probably just am better off just leaving out of the analysis, right? They don't have a representation of all my categories here. So this is one thing that you will forget to look at when you're going through and screening your data. But if we have categorical data, we want to make sure that we don't have outliers in terms of splits. They don't have to be exactly even 50-50, but if they're exceeding ratios of 9 to 1, we've got problems. For our continuous data, we have outliers operationalizes values with extreme standardized scores. We'll talk about standardized scores in the next lecture. But if you remember kind of standardized scores, this is basically read standardized scores as units of standard deviation. Conservative estimate, if I have scores that are more than about over 3 standard deviations from the mean, these are pretty extreme scores, right? If we think about a normal distribution, we should have less than 1.1% of the data falling outside 3 standard deviations above and below. If we get a score that's over 3 standard deviations from the mean, it should be probably suspect as, if not an outlier, at least an extreme score, okay? What we'll end up doing is taking a look at outliers with these standardized scores and supplementing with graphical methods. Thing to remember is with large samples, we're almost certainly going to have extreme scores, right? As our samples start to get 100, 200, we're going to get extreme scores because we're starting to get those people on the boundaries, right? We're going to collect those, so we shouldn't always necessarily freak out about it, right? Because it's going to happen, right? And luckily, in psychological science relative to other forms of research, other types of research, we tend to have less of an impact of outliers, just because our scales tend to be capped on by some arbitrary scale, right? Income can go on indefinitely, right? So you can get people way the hell out there, right? If my scores are put on a scale from 0 to 10, there's only so far you can get out of bounds for me, right? So issues with extreme outliers tend to be less common in psychological science, but for the purposes of running our statistics, making sure we have reasonable inferences, still want to go through and check, okay? So for getting these in SPSS, analytic descriptives, and then what we're going to do is we're going to save these variables in standardized values here. We're going to check this and hit OK. And then what we can do is SPSS is going to create a z-score for every variable that included that we requested it for, and then we can run descriptives on our z-scores and start to look at the minimum and the maximum, right? So here we've got a really low z-score, so we've got someone who clearly did not think that video was funny. Most people did. This person rated was 3 standard deviations, over 3 standard deviations below the mean in terms of how funny they thought the video was. But then we were also having here, and here people who, for some reason, found that to be the video to be anger-provoking, fear-provoking, made some people sad, made some people tense, right? And so these are scores that are scoring several standard deviations above the mean. Okay, we'll leave it at there. We're about done. We'll pick up these last ones next Wednesday. Okay, so any questions as you all are packing up and you can pack up and do your thing?